Good evening, I am Mr. S. Thank you for joining me. This serves as perhaps my last video I'll present on extreme values and the related topics, concavities and inflection points. This right here is a question from my past, perhaps 20 plus years ago when I was doing my calculus. This was a midterm exam question. I had to analyze this expression and it was rather difficult at the time. So I'm bringing the same equation out here in this video. It's an f of x is equal to natural log x divided by x. We have to analyze it with regards to extreme values, concavities, inflection point, all of that. Your original function is this. There's no interval provided, so you're looking here at the entire domain of this specific function. When you're looking at this right here, you have a vertical asymptote which will be x is equal to 0 because you can zero out the denominator with that value. If you're looking at this and you want to determine its root, you can take that entire expression and equal it to 0 and you'll determine your root, which is your x-intercept. And natural log x is equal to 0. This goes on the other side. X is equal to e to the power 0, which is equal to 1. 1 comma 0 is the root of this function, and we'll put this aside. Now we will do the first order derivative determination for this. Natural log x over x, it's a quotient rule. You'll do x times the derivative of natural log x, which is 1 over x, minus natural log x times the derivative of x, which is just a 1, all over x squared. The quotient rule. When you do this, you're getting a 1 minus natural log x over x squared. You can determine your critical points by making this equation equal to 0. When you make your first order derivative equal to 0 and you solve for the x values, you get your critical points. You have 1 minus natural log x over x squared is equal to 0. This goes on the other side, it's equal to 0. 1 minus natural log x is equal to 0. Natural log x minus is equal to minus 1. And then x is equal to e to the 1, which is e. You take that e value, you put in your original function, you get the corresponding y value, my critical point. There appears to be only a single critical point over here, but that's fine. You put e right over here, you're getting natural log e divided by e, which is what? 1 over e. My critical point x and y values are this, e comma 1 over e. You can get perspective by bringing out a calculator and calculating what this is. This will be like 0.3 something, this will be 2.71828. This right here represents my graph so far. I have a 1 comma 0 right here. And it's going to come from here because you have a vertical asymptote here. It's going to shoot up and it's going to come to this value, which is e comma 1 over e. That's what it is. If you were to look at this function natural log x over x and you were to divide everything by natural log x, you're getting here 1 over x over natural log x. Limit as x approaches infinity. You're doing something like a horizontal asymptote determination. You're doing 1 over infinity, which will be a 0. A horizontal asymptote will eventually develop right over here and your function will go along that. That right there represents a relatively modest version of what this function will look like. This horizontal asymptote determination is kind of like a cheat. It doesn't have to be 100% accurate horizontal asymptote, but it's helping me see what the graph curve looks like after this point right here. This critical point, it's going to be a relative extreme, some form, or an absolute extreme, but after this point I just did this little cheat in informal horizontal asymptote determination to see what the curve looks like from there. What do I have so far? I have a root, which is this. I have a critical point, which right here is that this critical point represents some form of an absolute or relative extreme, but we have to determine whether it's a maximum or minimum. I can do so by a second order derivative test. I can do the second order derivative of this original function, or I can do the next order derivative of this. When I do the next order derivative, I'm just doing the quotient rule again. I'm doing x squared times the derivative of this. This is my f function, g function. The derivative of that would be minus 1 over x. Minus, then I have my f function multiplied by the derivative of the g function, which will be 2x all over x squared, which is x to the 4. Simplify this. What are you getting? You're getting here a minus x. Then you're getting a minus, this 1 with this 2x is a minus 2x, then this minus is a positive, plus 2x natural log x over x to the power of 4. This right here represents my second order derivative. If I take this critical point x value and I put it here in places of this x, if I get a negative value, I'm looking here at a relative maximum. If I get a positive value, I'm getting a relative or a local minimum. If I were to put e's over here in place of x, I'm getting a minus e minus 2e plus 2e ln e over e to the 4. This ln e is a 1, that's a 2e That's a 2e minus 2e, that cancels out. I'm really looking at a minus e over e to the 4, which you can simplify, but you're looking at a minus divided by positive. Your outcome here is a minus. That tells you here you're looking here at a local maximum or a relative maximum. But that's exactly what it is. That extreme value is a local maximum, but it can also be something else. What is that something else? Let's talk about it. I'm keeping this second order derivative function right here because I'll need it. This right here, if this represents my entire domain, which is going to be really from 0 up to infinity, because negative values are not in the domain of a natural log. 0 is not the domain of this function because you have a vertical asymptote. This right here represents the entirety of my domain. Then this value here will be the highest point. It's a local max or a relative max. Local maximum, relative maximum, it's synonymous, but it's also an absolute maximum or a global maximum. It's both of these. This point right here, e comma 1 over e, is local maximum and global maximum, or you can say relative maximum and absolute maximum. Right now we've determined a root. We've determined another point which happens to be local and absolute, or you can say relative and absolute or global maximum. It's not a minimum by any means. It's the highest point of this function over its entire domain, 0 to infinity. Now what we need to do is determine the inflection point. The inflection point is determined as a change from a concavity down to a concavity up, or a concavity up to concavity down. Visually I'm seeing a concavity down. I could look down, it's a concavity, and then here I'm seeing a start of a concavity up. Consider this. You have something which looks like this, a full concavity, or you have something which looks like this and it stops. It still represents part of a concavity up, so you can picture the rest as being a concavity up, and you can call it entirely a concavity up. Why do I bring that? Because from wherever this inflection point will be, I'll have a start of a concavity up. Even though it level out against a horizontal asymptote, it will be the start of a concavity up. Therefore you can call that remaining portion a concavity up. The inflection point will help us delineate between the concavity down and concavity up. We indeed have both of those visually by looking at this. To determine the inflection point, the second order derivative where it equals 0 represents the conversion, in this case for a concavity down to concavity up. Here I have a concavity down. Here somewhere I have a concavity up. If I equal to this 0, I take this across, this becomes zeroed out. But what do I really have left? I have a minus 3x plus 2x natural log x is equal to 0. That's what comes out so far from this determination. If I take that 3x on the other side, minus 3x, I'm looking at a 2x, ln x is equal to 3x. And I have natural log x is equal to 3x divided by 2x, which is 3 over 2. X here is equal to e to the power of 3 over 2. That represents your x value of your inflection point. If you were to put this right here into your original function, which is what you would always do to get the corresponding y value, you'll get your inflection point coordinate pair. You'll do natural log e to the 3 over 2 over e to the 3 over 2. You can parenthesize this and bring this exponent right here by means of properties of logs. You're looking here at 3 over 2 natural log e, which is just a 1, over e to the 3 over 2. Which, if you manipulate this by means of denominators, you're looking at 3 divided by 2e to the 3 over 2. That's your corresponding y value. My inflection point has now been determined. It is equal to my x value, which is right here, e to the 3 over 2, and your y value, which is right here, 3 divided by 2e to the 3 over 2. That represents your inflection point, x value and your y value. Let's clean this up over here. You know how this determination occurred. You took your second order derivative function and you equaled it to 0 and you solved for x. Then you put that x value into your original function to get the corresponding y value, and that right there represents your inflection point. So right now we have determined the root, we've determined the critical point, we've determined an extreme which happened to be relative and absolute maximum. We've determined an inflection point which tells us we have a concavity down to concavity up. We know that by the graphic representation, but if you do the concavity test, look at this, it's e to the power of 3 over 2, and you know the domain is from 0, not including 0, up to infinity. Pick a value before this x value, pick a value after this x value right here, e to the 3 over 2. The value before it but between 0 will give you a negative in terms of your concavity test. Remember, the concavity test is this: if you plug in an x value of your interval of that concavity, if it's less than 0, you're looking at a concavity down into your second order derivative. If it's greater than 0, you're looking at a concavity up. Why am I picking a value less than e to the 3 over 2 and 0? Because that's my inflection point. It represents the transition from one concavity to the other. and a good value between that and 0 is a 1. When I put here, I'm looking at a value here of 1. When I put right here 1, you put it into this equation right here, you get a negative outcome. You can do it for yourself, it will be a negative outcome, which will tell you you do indeed have a concavity down for a value before this but after 0. If you take a value after that, you can take a value like what's e to the 3 over 2. It's something, let's see, 1.5, and then you exponential base, it's 4.48. Pick 5. If you were to pick a value, let's say 5, and you put it here to your second order derivative, you'll have a positive value, and that'll tell you you have a concavity up. And that's exactly what we have. A concavity down, concavity up. My inflection point is this. I need to get a good representation of what it was. 1.5, and then exponential base is 4.48. There'll be a value right over here somewhere. Here's my inflection point. It's rough estimation, but that's my inflection point. Remember my critical point E here is E 2.71828, and here I am looking at a 4.48. Of course, inflection point is after that global maximum or local maximum. That's my inflection point. I'm not worrying about the y value. It's 3 divided by 2 e to the 3 over 2, but it doesn't matter. It's more relevant with regards to the x value. Now all we have to do is just mark our concavity intervals, and that'll bring us to the end of this particular video. And you see now everything has come about. I'm erasing this part over here because you don't need to see it. Your concavity down interval is going to be what? From 0. It's never going to include 0, but it's going to be from after 0 up to e to the 3 over 2. Your concavity up is going to be from your x value of your inflection point, e to the 3 over 2, going all the way up to infinity, and positive infinity, and that'll be it. So in summary, we found the root, it was 1 comma 0, and it was good. We found our critical point, e comma 1 over e, which represented a local relative maximum, absolute global maximum, and that looks right to me. Then we found an inflection point, which is e to the 3 over 2 comma 3 divided by 2 e to the 3 over 2. That inflection point is good. We have a concavity down, we have a concavity up. It makes sense because the concavity test worked out. The concavity down is 0 comma e to the 3 over 2 interval, and then concavity up e to the 3 over 2 comma positive infinity. Everything is good. I didn't specifically show the first order derivative test, but I didn't need to because I used the second order derivative test to determine what type of extreme value this critical point was. If I wanted to use the first order derivative test, it would have been helpful to have a graph, and then I'm looking at the tangent lines. Here the tangent lines would go from a positive to a 0 to a minus, and in going from a positive to a minus, that indeed is a maximum, relative local maximum or absolute maximum. Within the narrow range around this point, it's a local relative maximum. Within the entire domain of this function, it's an absolute or global maximum. I won't say any more than that, but this right here was a question for my exam 20 plus years ago, and now I'm sharing it with you all. Thank you for watching. Have a good day.